Hello friends, welcome to my class of physics. Now today I shall discuss the complete structural analysis and derivation of optical fringe shift due to a thin transparent slab in case of Young's double slit experiment. Now you know in Young's double slit experiment is the foundation for demonstrating the wave nature of light via interference phenomena. Now in this standard setup there are two coherent light sources which generates alternating sequence of bright and dark fringe on the screen. Now when we introduce a thin transparent film or slab of mica or glass, and the thickness is T and refractive index is mu in one of the slits, then basically it alters the optical path length. So this introduce an additional phase difference between the two lights which coming out from the two different slits, and due to this the entire interference pattern shifts towards the side where the slab is introduced. Right, now let's understand that how we can define the optical path length. So when a light wave travels a physical distance x, which we can tell as geometrical distance, through a medium of refractive index mu, its speed reduces to suppose v, and this v is c by mu. So the time taken to traverse this medium will be x by v, and we can write mu x by c. So in this time, the distance light would travel in vacuum or air is basically called the optical path length, and that will be mu x, right? Now let's understand how to calculate the path difference introduced by the slab. So if the thickness of the slab is T and it is placed in front of the slit S1, then the light travels a distance T in the slab medium, and the remaining distance S1 P minus T will be in air. So effective optical path from S1 to P, that we call as delta 1, that will be S1P minus T plus mu T, and effective optical path from S2 to P will be S2P, that we can call as delta 2. So net path difference, if we write that is delta x, that will be delta 2 minus delta 1, and we are getting S2P minus S1P, then minus mu1 minus 1T. Okay, now from standard structural parameters of Young's double slit experiment, the capital D, that is the distance of the screen from the slit, that is very much greater than the small d. Small d is the distance between the two slits. So the path difference S2P minus S1P, geometrical path difference if we call as, so that will be d sine theta, and that we can write as d tan theta. So tan theta will be y by d, small y by d, so dy by d. Now substituting the value back into our effective path difference equation, so it will be delta x equal to dy by capital D minus mu minus 1t. Okay, so here one should note that if the transparent film is placed in front of upper slit, that is S1, the entire fringe configuration moves in that direction, that is the upward direction, and conversely if it is placed in front of lower slit, that is S2, the pattern moves downward. Now using this above equation, we can now find the new positions of maxima, minima and shift of the fringes. So let's see how we can calculate the new position of the central bright fringe. So we know that for central bright fringe, that is the 0th maxima, the path difference, net path difference is exactly 0. So if we put delta x equal to 0, that y we will write at y0, because that is the distance of the central fringe from the main center. So that will be dy0 by capital D minus mu1t, that is equal to 0, and we are getting y0 equal to capital D by small d multiplied by mu1 minus 1t. So this is the displacement of the central fringe, that is the fringe shift, and that we can tell as S, that is capital D by small d mu minus 1t. Okay. Now let's see how to find out the general position for nth maxima. Now for constructive interference, the net path difference will be n lambda, del x equal to n lambda. So if we use this, so yn, that is the position of the nth maxima, that will be n lambda capital D by small d plus capital D by d into mu minus 1t. Okay. Now let's compare the case where there is no slab and where we introduce slab. So the parameter property fringe width for standard configuration beta, we know that will be lambda capital D by d. Now when we introduce the slab, the beta prime remains unchanged, that is lambda capital D by d. Central maxima location, that will be located at the origin y equal to 0, and if we introduce the slab, we have seen it will be shifted by capital D by d into mu minus 1t. Fringe intensity profile, uniform symmetric intensity in case of where there is no slab. It will be identical in case of the slab if we assume that there is no absorption in the slab. Okay. So relationship to the fringe width beta, that is basically here the shift S can be expressed in terms of number of fringes shifted, that is capital N. So that will be capital S by beta. Okay. So that we will get mu minus 1t by lambda. So this basically allows rapid calculation of exactly how many fringe slots the structural grid has moved up or down. So in that case, this formula will help us. Now let's see a small numerical application. In a standard YDSE setup, capital D is 1.2 meter, small d, that is the slit width, distance between two slit, 0.4 millimeter, the monochromatic wavelength lambda, that is 600 nanometer, is utilized. If a thin mica sheet of thickness T equal to 1.8 micrometer and refractive index mu equal to 1.5 is placed over the upper slit, determine the physical linear shift of the central bright fringe. So for that, we have to use that shift equation, that is S equal to capital D by D mu minus 1t. So if we use these values, the distance of the screen from the slit D, capital D, is 1.2 meter. The distance between two slits is 0.4 millimeters, so 0.4 into 10 to the minus 3 meter. We have to convert everything to meter. Mu equal to 1.5 and T is 1.8 into 10 to the minus 6 meter, because T equal to 1.8 micrometer. So if we use all those values, so S will be 2.7 millimeter. So the entire fringe pattern shifts upward direction by 2.7 millimeter, because the that slab is placed over the upper slit, right? So this is all about. So thank you.